All right, guys, welcome to another episode of Robo Papers. Super happy today to have Eric Zixuan Chen, one of the authors from this paper called GMT, General Motion Tracking for Humanoid Whole Body Control. Thank you so much for making the time, Eric. Super happy that you can make the time. Maybe as a start, you can share a little bit about yourself.
My name is Zixuan, and you can also call me Eric. And I'm the incoming PhD student at UC San Diego, advised by Xiaolong. And my research mainly focuses on how to leverage learning-based methods to solve some fundamental problems in robotics, like whole body control or some manipulation and robot perception. And we can first see some videos here, which is the main demo of GMT. So as you can see, GMT is the abbreviation of general motion tracking for humanoid whole body control. So in this work, we are trying to solve a fundamental problem in humanoid control field. Which is general motion tracking, which means that we want to reproduce lots of human motions on a real humanoid robot. I think the core contribution of GMT is not about proposing a new algorithm, or we are working on a novel topic, but we are demonstrating that with good engineering and many other engineering techniques, we can solve a fundamental problem in the field of humanoid robots. As you can see, our method is mainly built on deep mimic, which was and this algorithm was proposed by Jason several years ago, and I think motion tracking problem has been well solved in the field of computer graphics, like PHC or mass mimic. They have demonstrated very high success rate on the very large human motion data set, but this still remains an open problem in the field of robotics. So GMT is trying to solve this kind of problems with so I think this work has pushed forward the the development of this problem in this field. Yeah. And as you
Yeah,
can see, this so the core of GMT is that we are trying to imitate diverse motions with one single policy. As you can see, the videos here, this is the non-scale sequences. Which means that we kind of stitched together several motion clips together, and then we can use GMT to track all of these motions. These motions are very distinct. Yeah. And you can see our policy has achieved very good results on this. And yeah, GMT I think GMT has also shown many has shown its abilities on many agile motions like kung fu, and it can also do some high kick, yeah, and soccer shoot. So yeah, and all of these motions are completed with one single policy, and we can also do some dancing here.
So could you talk a little bit about how you tell the robot what to do? Like, how do you set the goal for the policy? It's motion tracking for the a human reference trajectory, or what?
Yeah. So the goal of GMT is the goal of this policy is a window of motion targets, and these motion targets, they consist of the joint positions of each angle of the reference motion, and also they contain some root states of the reference trajectory. Yeah. So basically, the trajectories are obtained by human mocap data, and there's some and there are some and they some kind of fit the human embodiment. So we first do a motion retargeting to retarget that on the humanoid robot, and then we input this targets into the policy, and the policy can then track these targets to do all these kind of skills. Yeah.
yeah.
Cool.
Maybe Eric, it's if you want, we can switch to the paper.
Okay.
I know you have a couple of diagrams that I guess give an overview of the architecture.
Yeah.
Okay. Yeah. Great. Okay. So here's the PDF of the paper. So I think And as you can see, let's just dive into the meta section of GMT. As you can see, although we have like proposed several techniques to solve this problem, but I think the key to to a to a very good performance of motion tracking on real robot. I think the problems in GMT that we're trying to solve can be roughly divided into two categories. So the first category is about the data problem, and the second category is about the model problem. And by referring to the data problem, we're kind of like to get a so we're kind of like to so first we are trying to get a high quality motion motion data set for the policy to train on, and the second part is that we are trying to uh, we are trying to assign we're trying to sample more on those less frequent but very challenging motions. And by referring to the model problem, we're trying to improve the model capacity. Which means that we kind of change the model architecture, and the other part is that we are trying to do some careful designs on the motion inputs to enhance the model to improve the model architecture for better performance. Yeah, as you can see, as you can see from the framework here. So the first is that we have a so we have some mocap datasets, and in this paper is Nafan, and it is a combination of Nafan and AMAS, which are both like open source data motion datasets with very high quality. Yeah, and so first we are trying to get a motion a motion dataset with high quality. We're trying to do some so this process is what we call the dataset curation process, and dataset curation process is and its aim is to increase the motion quality of the training dataset. So what we're doing in the dataset curation process is that first we are trying to filter out some like invisible motions. And so what are invisible motions? And in this paper we refer to this as some motions that are that contain like crawling or falling states. Yeah, and because these are contact-rich motions, and as we and due to the limitations of the simulator, we need to we cannot like very conveniently handle all of this kind of motions, so we kind of like filter them out. And also some motions, they contain the object interaction or the environment interaction, like a robot is climbing up a ladder or climbing upstairs. And during training, we do not have ladders or we do not have stairs. And the reference motion will be just like the robot. So this kind of reference motion for the robots will be just like the root state is just like floating in the air out of nowhere. So we need to filter out these motions. And so during the first stage of the dataset creation process, we kind of we use a preset. We use some preset rules to filter out these motions. And but after this filtering, there are still some motions that are too dynamic for the robot to track, because and these motions, they are like spin kicking or like many other things. Yeah, and if and the robot cannot like produce enough torques to track these motions. So we just like train our policy on the filter motion dataset, and then we log the success rate of each motion, and we then filter out those and then we filter out those filter motions, and after this we get a high quality dataset. So by this way we can filter out some like extreme dynamic motions. And do you have any questions on this part?
Yeah, I mean, could you give us a sense like so Ames plus Lafani add together originally would be, let's say 100%, and then how after these two steps roughly how many percentage is left? Like, so you have 8,000, nearly 9,000 clips around 33 hours, but the original both data sets is altogether how big is it?
So the original dataset is about like 13,000 clips of motions. Yeah, so
I see.
we kind of filter out many motions. Yeah,
So actually, you only you filter out about like 25% of that,
yeah,
right?
yeah.
Okay, okay,
I think
mm.
it's around like 20% of the
20%.
motions.
Okay, cool, cool, cool.
Okay,
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 right,
yeah.
right, cool.
Yeah. And so after this filtering, we so we need to by this data set creation process, we can improve the training quality on the of the motion data set. And another part is about the adaptive sampling. We're also trying to solve the data problem. And adaptive sampling is, I think, it's kind of like to make the policy to train more on those less frequent but challenging motions. And a motivation of adaptive sampling is that we can look at this figure. So we kind of use a large language model to annotate what each clip of the motion is doing, and by I mean by looking at this figure, we can see that almost like 80% of the AMS dataset consists of basic skills like walking or in place or some in place movements. Yeah, so which means if you train all the motion, if you sample all the motions uniformly, you can your policy would like train mostly on this like walking or some like in place basic skills. But we also want the policy to do some to do like some dance or jump or kick or squatting. Yeah, and this might pose some problems, and that kind of like explains why like so many previous works they have like failed to get a they have failed to show various skills with one single policy. Yeah, so I think this dataset distribution actually affects a lot on the training quality. So based on this observation, we propose the adaptive sampling, and adaptive sampling, as you can see, mainly consists of two parts. So the first part is that we first random clip all of the motion clips, and this is based on the another observation that motions like in AMAS, the duration of each motion clip is very uneven. So some motion clips are very short, like and then they last for only like for several seconds, but other motions they are like very long. They might last for several minutes. So and for those non-motions, they are like often composite motions. So which means they consist of some simple skills and also some hard skills. And your policy might fail on those harder parts, but if you just increase the sampling probability on that on this single motion clip, then your policy might like train might also like repeatedly train on some like simple parts, so that can hinder the learning efficiency. We kind of like random clip the motion into evenness, like around 10 seconds to make to make this to make their duration like very close. And after this clipping, and so during training, we log the tracking error of each motion clip, and then we kind of increase the sampling probability. So this is just a formula, and the intuition behind that is we increase the sampling probability on those motions with a larger tracking error, and we assign a higher sampling probability. So which makes our policy to train more on those motions, and then our policy can capture some like harder motions like kicking or jumping. Yeah, these dynamic motions, and they appear less frequently, but we sample more, so that kind of like compensate for the less frequent. Yeah, and this is about the adaptive sampling. So with this creation and with adaptive sampling, we kind of like so we kind of address so we kind of aim to address the dataset problem, and we so yeah and yeah.
Sorry, Eric, I'm curious. Like, did you guys like maybe just look into some of those? Are there any clips that you thought is quite simple, but then somehow like the tracking error, it ends up being in this bucket of considering difficult, or
Yeah,
is
so
broadly speaking, everything you see there, you kind of expect, oh, okay, these look difficult. I'm just curious.
Yeah, so I think this is a very good question because when we look at the tracking error, after we train this policy, we kind of it's just expect because some motions that are less frequent, but they are they are supposed to be like less difficult, like stomping. Yeah, because stomping is just another variation of walking, but our policy does not like perform very well on stomping motions. So I guess like stomping may appear very less frequently in the whole data set, as I can only like observe only a few clips they contain this kind of skill. Yeah, so yeah, I think this kind of so I think this is a so I think our like adaptive sampling still have some limitations because as it cannot handle those motion clips that appear that very less frequent. Yeah, so I think I think this still has some limitations.
Got it. Cool. Well,
Makes
I mean,
sense.
I think it's a great way to quantify things, right? Because like if you, so that's where I think maybe in human intuition may never like translate directly. Like as you say, stomping sounds like walking. It's just like heavier walking, maybe.
Yeah. It's just heavy walking.
But by doing so, basically you sample that more frequently to hopefully then downstream you improve on the policy. Okay, that's awesome. All right, cool.
Yeah.
Yep.
Are there any like implications to which tasks end up in the distribution? Like if you end up with lots of tasks that are sort of like I understand that you're doing some selective sampling and rebalancing the data set and all of this, but like I could still end up with like 5 tasks that share some particular stereotyped motion, like 5 different types of kicks or something like that. And like, did you end up having to do anything to account for that kind of data issue, or that just doesn't come up in AMAS or not important? Does that question make sense? Yeah.
I'm not sure. So can you repeat your question again? I'm not sure.
So
I
if
get
you
that. Yeah.
so the point of doing all of this sampling for like different tasks, right, is to make sure that you've got like, I assume it's to make sure that you've got like good coverage of the different types of motions you might be asked to do at test time, right? So like, and you're removing all these biases in the data set. But like, I guess the question is, how do you know whether or not you've done a good job with that? Because like, what if I have like 5 different subtasks that all share some particular same motion patterns? Does that make sense? So that like they all like look very, so that the robot doesn't, so that like, how do you know whether or not you've actually got enough coverage with this sampling, with this retuning? Does that make sense?
Yeah. So this is I think this is a very good question. And right now the metric we have right now is only the max key-body error. Yeah.
Okay.
So we just log the tracking error, and we assume that if the tracking error is nil, and then the policy might do a good job at tracking these motions.
Okay. Do you have like a validation set or something during text time? Or like, I guess, all right, that makes sense.
Yeah, we have some validation test. Yeah, we kind of like follow the setting of PHC. So as you can see here, we kind of like evaluate our policies on the test set of AMAS dataset. So which just like consists of like 10% of the whole AMAS dataset, and we use this kind of dataset for validation, and we do not include these motions for training.
Yeah. Okay. So we don't need to we can get to this later, maybe when we go to experiments, but I'm really curious as to whether or not like AMAS and LaFan datasets have like enough coverage to do any arbitrary task. So like, but we can, maybe that's better to talk about later when you get to your experiments.
Okay. Yeah. Great.
Like, okay.
Okay. So we can dive into the model part here. For the model, we were talking about the model. We are trying to improve the model capacity, and we'll also do some careful designs on the model input. So let's first talk about the model capacity. So instead of like we just use a simple MMP network, so which was adopted by many previous works like XBody2 or OmniH2. So this works. They only use a simple MMP network, and we assume that as long as we are working on we are working on the large motion dataset, and MLP may fail to capture the distribution of all kinds of motions. So we are trying to improve this model expressiveness by replacing the simple MLP into a motion MOE. Yeah, so this MOE architecture we are adopting is just a simple is a soft MOE architecture. So which means we train like several experts, and we also train getting network end to end together to get the output. And the output action is just a weighted combination of the getting network output and also the expert output. Yeah, and by combining this weightedly, we can get a final action. Yeah, which is used for and we have assumed that this kind of motion MOE has need to a performance improvement on the motion tracking. And I think the basic intuition behind this motion MOE is that it's based on the observation from Xbody tool. So which Xbody tool report that if we train a policy that's on the same motion category, like for example, if we train one policy for walking and we train another policy for all of the jumping, and the performance tend to be better. So we kind of assume that that different experts can handle like different motion types. And that is the basic motivation why we use this motion MOE to increase the model capacity. Yeah, and another part is about the we do some like careful designs on the motion input. So the motion input, the first is that we are trying to use a local representation of the motion input, and this is in contrast to the to previous works in graphics or in like Omni H2O. Yeah, they kind of adopt they kind of use the global position of the motion, and they make the robot to track the global position of the motion. And the reason why we do not use the global position is that we observe that if we use a global position, the performance can be worse. And this can be explained that we have to retarget the human motion into our robot, and this retargeting process they might have some errors. The global position of the motion, they somehow contain the information of the velocity. Right. So by tracking the global position, we need to assume that every step the robot should track well to should track the velocity very well, but actually on the after retargeting on this we might get a accumulation error, and the robot cannot like produce enough torques to follow that velocity. So we just use the you use another velocity tracking reward, and also we use the local representation to solve this problem, because you can like tolerate some like velocity errors during like velocity tracking. Yeah. Instead of considering it as a hard constraint. And another thing that we surprisingly found very important is actually the motion input. So instead of previous works like Xbody 2 or Omni H2O, they only use like one single frame into the policy, and in GMT we use we use a non-window, so we use like a future like 2 seconds of the motion and as the input into that policy. So and besides this, we also like explicitly input the next frame into the actor network. So and as the network, you can see here a structure can be expressed like this. So first we like so we have 2 seconds of window, and we compressed it with a convolutional network, and then we also input the immediate next target into the policy network. Yeah. So what is input into the policy is a latent vector and also one like explicit frame here. So and this kind of like improve the performance a lot. And the intuition behind this is that why we input a null window is that we can think of ourselves as humans. When we need to do something, so when we need to do something, we need to like first prepare ourselves. We need to first aware of what we need to do like for the future. Like we want to jump, we might adjust ourselves ahead to jump. And I think this is the same case for the robot. And a more scientific explanation is that you input a window into the robot, so the robot can know so the robot can know which clip it is imitating on. Yeah, and we also like input the explicit one single motion into the network, and this is because this is because like during compression there are some like information loss, and the next target is always the most important for the robot, because that's the robot need to track out immediately. So so we also like input this explicitly into the policy network. Yeah, and
Sorry, so that makes a lot of sense. This is really interesting. But like one question. So when you're when you're setting the trajectories in, so these trajectories are from like your motion reference, right? That you want the robot to follow. So like what happens? So how do you actually execute? So like the robot's at some particular position. Like what if it diverges for whatever reason from the trajectory? Like is there just going to be this gap between what it's trying to do and where the robot actually is? Does it not actually come up? Does that question make sense? I don't know.
Yeah. I think there are also like some gap between the robot and the reference motion. But but as you can see, we have some like termination process during training. Like if the robot deviates from the reference trajectory too much, then we terminate this episode. So the robot can motions of the robot can always like fall on this trajectory to get a better
so this is like so it always stays within some like executable like cylinder of wherever the robot the real trajectory is supposed to be, I guess. Is that kind of that's the answer then? Like it will terminate if it doesn't. Okay, that makes sense. Cool, thanks.
Yeah. And that's something that we call early termination. Which was also the technique proposed in DeepMind.
No, it makes sense. Yes.
Yeah. And
that's right.
Yeah. Sorry, okay. Eric. Yeah, I'm just curious. Did you guys try maybe different, like instead of 100 like or 2 seconds, do you try like 1 second, like 3 seconds, or?
Yeah, sure.
You guys didn't do.
Yeah. And as you can see from the table here, we like in our experiments part we have tried, and this L2 means that the window is 2 seconds, and L1 is 1 second, and 0.5, and so on. Yeah, and with M is that we input the next frame as the next immediate frame explicit to the policy network. Yeah, and we have found that actually 2 seconds can get a better performance. We also like tried a longer window, like 3 seconds or 4 seconds, but then the input frames will be the input window will be too long, and you have to increase your model size to process that, and that can lead to the training time increases, and also like during deployment it can cause some problems. Yeah. So I think like 2 seconds can is somehow strike a balance between the efficiency and also the performance.
Yeah, I think it's like, really cool in that. Sorry, Chris.
Oh, no, so, by performance, you mean like inference time is too slow, or like actually like the performance the actual like success rate starts to drop, or which one? Yeah. or both?
Yeah, I think the success rate can slightly increases if we use a
Okay.
longer window, but that increase just is not that very it's not that obvious. Yeah,
It's not worth
yeah,
it.
and
Okay.
yeah, and the inference time can be and the inference can be slower, and because like during deployment we need to make our policy to inference at
Okay.
and
Yeah, that makes sense.
yeah.
Yeah, I'm just trying to intuit this back to like what I do as a human, right? Probably, I mean, obviously
Okay.
we move around the world mostly subconsciously. We don't think about this thing. But if I really were to think about it, like how I actually do it, let's say like moving my arms like that, I'm probably making one decision every say 50 milliseconds, so maybe around 50 hertz, right? Or
Yeah.
lower than 50 hertz. But then also projecting maybe up to 1 to 2 seconds, and then
Yeah.
I mean, whether you're playing a football game or basketball game, I mean, effectively you are making very, very like on a rolling basis, a short window into the future, but then adjusting accordingly. Then, and then of course you have the next. The most important is the next action that I'm about to do in the next decision step, which is I guess your M, right? You denote it here. Yeah. So I think it makes a lot of intuitive sense. Yeah, that's probably how human actually do it. Yeah.
Yeah.
Cool.
Yeah. So this kind of like adapted intuition adapted from humans. Yeah.
Cool.
Yeah, and yeah, I think so. Those are like many the meta parts of the GMT. Yeah, I think with so with this like techniques we can get a better performance, like state of the art performance, compared with previous on motion tracking. Yeah, and
Yeah.
yeah, and here's the some like experiment parts. So for the experiments, we're mainly like do something like the ablation study. Yeah, so we first ablate the input window of the the input window length and also our like so input the immediate next frame into the policy network, and we can found that our trick has achieved the better has achieved the best performance. And also we update on the adaptive sampling and also the MOE architecture, and we found that both parts have led to like have led to very important have contributed a lot to the overall performance. And also we have like compared our work with X42. So we just like train the X42. So we just scale up the training data set of X42, and we found X42 actually actually performs worse than ours. Yeah. And by looking at this figure, like this figure 4, so we knock the so we kind of knock the gating network output of each expert like during one motion clip. So this motion clip is as you can see from the figure, is just a robot standing place, and then it walks forward and keeps up high and then walks backward. Yeah, and as you can see, like during different stage of this motion execution, the gating network output can be like very different for each kind of skills. So this kind of like show our MOE has like different experts have like different specializations on like different skills, and also like okay.
Sorry, Eric. How many experts do you have in this?
So in this work, we just use like 6 experts.
Interesting. So it's like what you're showing here is maybe at the moment when it's about to kick up, maybe the green experts start to step in, but then when it's doing something else, maybe stepping back and the purple experts step in and do more.
Yeah.
Interesting.
Yeah.
And do you have any intuition about, yeah, it seems that there's a lot of parameters that you probably have to twin, like you say, a lot of engineering work put into this. Do you have any intuition like what if you pull more experts like?
Yeah, we have tried like more experts like 8 or 10, but again it's also it's the problem of it's the problem of trade-off between the efficiency and also the performance. Yeah, and we have like achieved somewhat a slightly better performance with like 8 or 10 experts, but as you can see, when adding an expert, you are basically adding another network into your overall policy network. So that might increase the policy that might increase the model size and then increase the training time. Yeah.
Could you state again? So I guess especially for the in real world kind of evaluation, the policy that you run is running on the device in the robot, right? In the G1, right?
Yeah.
What kind of compute does that have?
So it has an O-ring on the
Mm-hmm.
on board. Yeah. And we kind of influence all our policy on board.
I mean, it's but what you're saying suggests that I guess I mean obviously this the compute will just get better over time, right? Like maybe the G10, I don't know, by the time the 10th generation come around, okay, then maybe you don't have to make. Well, the current trade-off you are making in a way is limited by the compute that you have on the robot, right? Yeah. Okay.
Yeah,
So this will only get.
I always believe that if we have a better like onboard computing,
Mhm.
or somehow we can compute our policies in the cloud, and then we can try some like other powerful control models to see if it can like perform better on this. Yeah. But right now we are using somehow like NLP or a very simple network. It's just I think it's just a trade-off on the computing resources here.
Got it.
Okay, yeah. And as you can see from the figure 5 here, this is another part of the ablation. We kind of like log the tracking errors, like different tracking errors, of GMT, and also without adaptive sampling, although without MOE. And as you can see, like here, top 5% or top 10% is the top percent error of the on the whole MS dataset. It's that the like top 5% error is the difference of top 5% error is very significant, as GMT can like with adaptive sampling, also with like MOE, we can somehow improve the performance very significantly on those more challenging motions, and that is also the goal of GMT here.
Sorry. Can I ask you a question, Eric? Could you zoom
Okay.
into one of the, let's say, the key body? Could you zoom in a little bit to that chart in key body?
Oh yeah. Let me clarify on this key body. So the key body is that we is because the robot has like many rigid is kind of the a tree of different rigid bodies, and key bodies means here like we select a subset of the rigid body, like the head or the elbow or the wrist, the waist and the knee. Yeah. And we select a subset of these bodies because we assume that this subset of bodies are very important for the robot to get a better performance on tracking. So yeah, we
Got it.
log the tracking error of these key bodies.
Sorry, could you actually zoom into the chart? Like I can't quite make out. So one is top 5% or something. Yeah. So what you are saying here, let's say under the key body, the top 50%, this is tracking error, right? So the lower the better. And I guess you care about the top 5%. So it's as if the top 5% are the edge cases.
Sorry, what the key?
So you group by top 5%, top 10%, top 20. Could you explain what are those again?
Yeah, these are kind of like the top 5% tracking error, top 10% tracking error. Yeah. So which means like so which means we rank all of the tracking errors in an order, and then we give like those top 5% large tracking errors and top 10% large tracking errors. Yeah, it's kind of like a percentile.
Yeah, got it. So I would say over time, what matters is, I suppose, at the edges, right? So maybe the top 5% is where you will focus your energy the most. Would you say so?
I would say so. Yeah, because as you can see, because as we have like demonstrated in this figure, like most of the motion, most of the motions from the motion from the dataset that we're training on, they consist of walking and in-place motions. And you can see as X-Body 2 or like many previous works, they have already done a very good job on these basic skills like walking, and walking, and also they can do some like in place motions, but they cannot do some like hard motion, some challenging motions like jumping or kicking. So, and this top 5% or top 10% is this jumping and kicking skills, and we are trying to get a better performance on these motions.
So it's like future work is trying to get jumping and kicking kind of stuff to work.
Yeah.
So these are the AMAS tests, right? The held out tasks. Or
yeah. So these are the home MS test.
Yeah. Oh, these are the whole data set.
Yeah.
But okay. That makes sense.
Okay. Yeah. And for the chart, we just use the test set of the AMAS of AMAS. Yeah. Because like after averaging, because for the whole AMAS data set, there are many like simple motions. Both that like all of your policies can work very well, and after averaging, your advantage may not be that significant.
Yeah. Okay. Curious, like, did you compare any of these against like just Deep Mimic? Like, how well does it do on these things against? Like, what's the tracking error comparison between like something that's in your training set versus something in Deep versus if you ran Deep Mimic on that?
Yeah. So, do you mean that we compare our work with the Mimic or like many?
Yeah.
Previous
I'm
works?
just curious. Like, yeah.
Yeah. So we do not like compare our works to those works in graphics, because works in graphics, they kind of use so their policy has the access to the to some like private information like linear velocity of the robot, and we cannot access this in our setting, so we do not compare our works to them, and here is another downstream application of our policy here. So we use MDM, which is the motion diffusion model, and we have some like text input, and then this MDM can generate some motions, and then we try to test our policy on this MDM generated motions, and the result, as you can see, is somewhat very good. These motions are, and they did not appear during the training time, and they have like some like very distinct distributions of the training data set, and our policy can do this skills like bowing or crouching, and some like sitting, so this is very well, and so I think that's the main part. So I think that they are the main parts of the paper. So we are trying to solve a fundamental problem in robotics, and in the future, we hope that we can integrate more skills into our policy, to like even like getting up from the ground or do some like more crazy skills.
Very cool.
Eric, I'm curious about like, could you talk a little bit more about your experience when you guys were trying to do this in the real world, like deployment? I don't know how many G1s do you have. Some of the moves that you do are pretty crazy. Like I saw the one that it's almost a kick and like kick one leg and then but the other leg look as if it left the ground for like a split second. Or like, oh my gosh. Could you comment about those? Like I mean, it's because everything is just from one single policy, right? Like, what kind of motion do you even know that you can possibly even try? I mean, of course, you can try in simulation, but you don't want to break your G1. So, how do you make that judgment call?
So this is a very good question, because so the motions, I think we're trying to do, so we have a pipeline. So we first like train our policy in simulation, and then we might validate in module code. So since our policy net is trained on SRGym, one simulator, and then we validate it on another simulator, and like module code, because module code is more close to the real world, and we kind of knock all of the torque inputs during the sim to sim transfer of Mujoko, and we need to and we need to like make sure that each torque output of the robot of the policy in simulation should not be like too large, so it should be like lower than the 80% of the torque limit. So and for this kind of motions, we can try our deployment on a real humanoid robot. But yeah, so and we're afraid of breaking our robot, so we do not like try some like even crazier motions. Yeah, some like so our policy in simulation can actually jump very high, but we we didn't dare to try that. Yeah.
Yeah, I imagine like okay, so you have this so-called sim to sim stage where you in mutual code you check all the torque value, make sure that probably in real world it's gonna do
Yeah.
it with some tolerance probably.
Yeah.
Did you try like I don't know, stressing your hardware a little bit, maybe like keep doing the punching until like maybe one of the servos starts to overheat? I'm curious, like have you stretched the physical hardware to that limit before, or
Yeah.
you just
We have tried this. So we have tried this, and our observation is that on the current G1, if we keep like doing, if we keep rolling our policy, on this G1, and we do some like very dynamic motions like kicking, or like this kind of skills, so they can not do this for more than like 4 or 5 minutes, I think. Yeah. So after like 4 or 5 minutes, the motor will overheat, and the performance will like degrade very very drastically, and the robot can fail.
got it? Yeah, I think it'll
So
be
so I think the hardware limitation is still like very important if we want to get a better performance.
yeah. It strikes me that like I mean, as you said earlier, probably the compute in the robot is gonna improve. So the intelligence is gonna improve, right?
Yeah.
Even without any new research breakthrough, just on this path, having better hardware, you probably can have better brain. But then
Sure.
if the hardware, so hardware actually will become like a big bottleneck towards things.
Yeah.
So yeah, maybe this is some of the things that you're about to talk. But I was just thinking, in order for these things to really ultimately work in the real world, it's a little bit like, if when anyone doing sports, after a while you know your own body, right? Okay, if I'm at my limit, I'll rest for a while, or like, so I'm aware what is my limit, right? Whereas right now these models, they're just too until they literally fail, right?
Yeah.
Like, so I think having that literally feedback from like how the hardware is doing will be probably something that's kind of required. Yeah.
Yeah. So
Because
we
right now,
do
in a
not.
way,
Yeah.
you are playing at a little bit like a almost like a pre choreographed thing, but without
Yeah.
knowing what state the robot is in. And when I say state, meaning the hardware like condition.
Yeah.
But still extremely impressive. Really, really cool. So, yeah, but maybe you can talk a little bit about the limitations and then some future work. I think good.
So I think the limitations, as we can see, the future work can be roughly that divided into two parts. So the first part is that we're trying to, so it's about the policy itself, that we can integrate more skills into the policy, and we can to enable our policies abilities on challenging terrains, on some like rough terrains, to make a policy to work on like different scenarios. And another part is about the autonomous. So we can somehow get a high-level planner. This planner can be based on this planner can be a motion generator. It can based on the perception input or the command input. So for example, if we want the robot to pick up to grab some on the table, and then this planner can like generate motions. So the first, it can generate motions that guides the robot to walk towards the table and then grasp something up. So I think this kind of like we can integrate the high-level planner to generate motions for the robot to track, and then we can perform some skills autonomously. And we can also like do some next like text to motion. Also, we have some like a text-based motion generator, and we can generate some motions for the robot to track, and then the robot can do like different skills. So I think GMT can be kind of like function as a node-level controller, and all we need to do is a high-level planner, and then we can do some tasks to enable general robots.
Nice. Makes sense.
Yeah, makes a lot of sense. Because right now, like GMT is like someone who's really good at doing motion, but basically blindfolded in a way. Like it's like doing all sorts of motion, but closing his own eyes. But once you give it more vision, and then it can start to interact with the rail, and then especially when it's terrain aware. I imagine you can really like use GMT to actually execute actual motions from a higher planet. Yeah, it makes a lot of sense. Any particular skill? So you mentioned skill. Do you have like concrete examples that you love to see, maybe in a follow-up work that you would love a plan to be able to do?
Yeah, I think for the next step, I think we can first so we can develop somehow that we call the motion generator, a high level planner, and that can guide the robot to do different so that you can avoid the obstacle dynamically, and also like you can do some like simple local manipulation tasks like squatting down or grasping something, and this kind of skills they do not need. They don't require very high precision, but yeah, I think they are a very good application of the next step of GMT.
Yeah, it'd be cool to eventually get a humanoid to go through one of those like obstacle course, those like those you see on TV, those crazy athlete go through obstacle course. Yeah,
right.
Yeah, I imagine we need something like GMT. That's really cool, man. Okay, yeah. I guess maybe as a wrap up, are there any like recent? Doesn't have to be recent. I guess any papers that you've come across that really piqued your interest that you want to give a shout out?
So the first work would be another work that I also like participated in. Yeah, which is Twist. I think you have also like featured this in your channel before. So I think Twist can be like Twist kind of like do the whole body teleoperation real time on a real humanoid robot, and what nice on the basis of Twist is also a general motion tracking policy, and this policy it can be like improved with some skills of GMT, and it can like achieve better performance. And another work that I'm mainly interested in that I'm impressed is called Clone. So it is another like teleoperation, but different from Twist. It just use a VR head and Apple Vision Pro. So which means it has only like access to like 3 sparse key point input to the robot. But as you can see, the robot can do like all the different of skills like squatting down or walking like human, and even like sidewalk. And they can do this real world teleoperation in the wild, in different scenarios. I think that's very impressive because they're like the overall system delay is very low, and they can policy is very robust. I think that they are quite impressive.
That's awesome. Yeah, so we covered Twist already, and then Clone, the episode is coming quite soon. So
great.
That's awesome. That's awesome. Okay, cool. Well, anyway, thank you so much for your time.
Okay, thank
Chris,
you.
I don't know whether you have more questions.
No, I'm good. Yeah, very great work. Really cool videos. Really nice stuff. Thank you. Yeah.
Okay, thank you.
Cool. Well,
Thank you.
thank you so much for making the time, Eric. It's been a pleasure having you share your work.
Sure.
Okay, Chris, what have you learned today?
Yeah. So GMT, so as they learned like a general purpose policy for motion tracking for doing on, I really liked the videos that he was able to show us at the beginning, in particular, like really cool, really dynamic motions. Like a lot of the times with these like Unitree kind of robot demos that you see, like it's a policy train for one thing. It's very cool that this is like it can do a wide variety of different tasks. I thought that it's telling and interesting, in my opinion, that a lot of the work that they did was like this data set curation and cleaning and balancing, because like so many of these things come down to data and getting everything right. And of course they had a whole bunch of algorithmic stuff too. It's all really interesting work. What did you think?
Yeah, I think to your point, like to get to really cool demos like those that they've done, actually behind it is a lot of engineering effort. As you talk through the whole pipeline, like there are so many things to tune, right? Down to, let's say the adaptive sampling. I saw a few exact number like 0.15 and then 1 to the power 5, like this kind of thing, like deciding what should be sampled more. I'm sure there's a lot of like things that they've tried, like number of experts in the mixture experts. I do want to say that mixture experts remind me a little bit about literally the episode that we recorded yesterday with the guys from R2S2, because they have something like skills ensembling. Is it like similar thing actually? Is it, if you recall?
I'm trying to say
they have the primitive skill.
I do. I think it's sort of different actually. So I think
it's different? Okay.
Yeah, because mixture of experts. So the skill ensembling is like, it's more implicit, right? It's saying like one model should be able to do all of these different things. The mixture of experts creates like parallel pathways through the model, kind of, right? Like it's kind of like one is saying like all these vertical skills, and one of these are like these are all the different ways that the model can evaluate policies. Right? I don't know. Yeah.
I see.
Yeah.
Yeah, I guess I see what you're saying. So yeah, maybe it's a level of abstraction at which stage. So it seems to me out to S2 they're thinking about primitive skill, like okay, let's say locomotion is one skill, and then what's the other one? Like
like
a body adjustment.
One was reaching, like hand pose reaching. Yeah. One of them was one of this torso tilt, right? And they all had different degrees of freedom, right? So it was actually like composition of a bunch of different things that could all happen at once, right? Whereas this is vertically like saying it's useful if there are different pathways through the model that specialize differently. And that's actually something there. I'm trying to remember the name, but we have had a couple others that talked about mixture of experts, and I am just
that's right.
Yeah, and it's also like there's just like the Kimi K2 model that came out, which is like this 1 trillion mixture of experts model, right? I think that kind of stuff is it seems to be popping up everywhere now. I think anyway.
Yeah.
So
it's interesting. I mean, in a way, this so-called mixture of experts, you don't get a human to predefine what are the experts, right? I mean, whereas in the case for R2 S2, at least the paper yesterday, they Li Yi and the team, they actually, I mean, as a human, you know that okay, like body adjustment is a one primitive skill and you work towards that. So so you have that maybe shortcut based on human intuition. I wonder which one it's. But well, in any case, I mean, I thought that the pipeline that is described in GMT very scalable. I feel like it's scalable in that you don't need to like throw in more data. You just, as the compute improve on the robot, like you probably just get even better. Yeah,
they seemed extremely limited by compute, actually, right? Like the 2-second look ahead window, whereas basically any amount of look ahead would improve performance. Like it seemed to like it, but like the mixture of experts thing increases inference time. So you would need to trade off with increasing the number. Decreases inference time, whereas the length increases it. So so like with a huge GPU, if they had like a Jetson or I don't know what they have on the robot, but if they had more compute, I think they'd do much better.
Yeah, right? But I mean, these things will naturally improve with as the hardware generations come about. Like same amount of power from the battery, probably. Yeah, so this will just naturally. I guess so long, and then in this pipeline they have almost like a safety precaution thing where they test things out in simulation, make sure the torques are all within bounds before they apply, and then so I have a feeling that by the time they actually do it in the real world, they probably have a recipe where they feel, okay, if this work past the test, this probably will work zero shot. And I think that's why they managed to get so many motion, because it's kind of tested, even though they probably have only 1 or 2 G1s. But for them to have so many variety, it means that they actually have a pipeline to do that final test, I kind of feel.
How many G1s have you broken so far?
Oh gosh, dude! I mean, the fighting. I mean, G1 and G1s. And these things overheat. That's why I was asking. So actually, it seems to me, I mean, that's the thing with real world robotics. Like,
you break a lot of robots.
Yes, you. I'm sure you've been to so many different labs, right? Like one thing that struck me, I visit quite a lot of labs nowadays. Like most of the time, when I ask the researchers, hey, what's this robot doing here? What's this robot doing? Like half the time, the robots are under repair. And so
it's actually good though. Like I feel like when I was in grad school, like you had one robot that everyone shared, and if that broke, you were screwed. you were not publishing your paper. Like
that's true. But I would say some of these labs that I go to, they are quite well endowed, right? So it's different. It's
different now. I think things are changing.
Things are changing a little bit
for the better.
But still, I mean, it's super annoying when robots break down, man. Seriously, like So. Yeah, that could be a really, really big bottleneck. Like, I mean, it could be the AI runs so far ahead that, but if the robots can't do it, the robots can't do it. It's like,
They can do some impressive stuff, though. They're good. Yeah.
True. Yeah, I mean,
I also do wonder how much of it is
sure.
like because it's also like the ways that the robot is accomplishing these different things, like the motions that it is making are ones that are hard for the robot. Like I bet you could find better ways of dancing, right? That wouldn't put so much strain on the motors, right? Don't do you, I mean, you've used the injury more than me, which is I have 0.
Yeah.
So, but I would think that like because this is one of these things where they're tracking human data sets, right? And as much as it is a humanoid, it is not human. It has different, like the joints are slightly different, the size is different, the motors are different. It's trying to do things that may not actually be the hips are slightly different, like mounting positions. It's trying to do things that aren't necessarily natural for it, right? It would be like, I don't know, if you were trying to dance like a gorilla, I don't know, something with different kinematics than you, right? Like,
yeah, actually that's a good point. So it could be that the tracking error would never be 0 because of that. And so, but in fact, maybe you might be overshooting yourself if you are just looking at that as So, but I mean, but clearly, I mean, the demos themselves, they're
really cool.
Proves that you can do already so many of these like really cool motions. I would say though, like from the hardware in general, what I've observed, like all these humanoids, right? Usually the shoulder, you can imagine like
the shoulder is a problem.
It takes takes the weight of the entire armor. So if your arm do a lot of things, like these two are fine, but your shoulder needs to be a lot more. It is definitely. I think it's definitely a more powerful servos actuated on the shoulder. But still, I mean they do warm up quite quickly, or heat up or get overheated.
I wonder if those get better. I wonder if they like come out with like 10 different robots or some different types of humanoids, right? Like there's the clone robots. No, those are a terrible example. But like there may be other technological innovations that help us work too, right? Because like we don't have direct drive motors just in our shoulder, right? Our shoulder muscle is huge, it covers most of our back, right? So like that's we just don't. This is like what I'm saying. Robots are just like the physics of a robot is so different from a human that sometimes the limitations like this are not intuitive, I would say, right? I don't know. Anyway, it's a huge tangent from his, but it's relevant to why they break robots, right? Or why?
We should really try to get like hardware people to come on the show, once in a while to talk about hardware stuff. Like my biggest thing about humanoid is exactly like you said, right? I mean, if you look at not just human, but most animals, in fact, all animals probably, like our joints. That's not where the actuator is, right? The actuator is our core, right? The actuator is here, right?
Yeah.
Right. So this is just a pivot, right? With tendons and cables going through. So whereas in the morphology with all the humanoids actuator is not at the joints. There's nothing in this part, right? This is just like a piece of metal, right?
Oh, you're right. Like so your hand, right? Like you can see, like if I move my fingers, like the muscles go all the way down here, right? Like
exactly. The
your hand is
here.
all the way down here. It's not like with these direct drive things. It's all like right here.
Yeah, exactly.
Like, it's just so different. Yeah.
So
anyway,
and actually it has safety implication as well. I mean, because if you have an actuator at the joints, angular motion momentum is going to be bigger, and then harder for it to stop. I mean, so the fact that it can do all this despite like the direct drive, it's already quite amazing. But I can imagine totally like it's a big strain on all these servos, so way more than what human muscles. Because I think we are just mechanically more compliant, right? That way. We have a much more spread out like kind of actuators than like they have one that's the energy all like in this one thing. Anyway, but it's a tangent. But we should get the folks that do actually hardware stuff to come on.
There's a bunch of we should do that. We can do that.
Yeah, we should do that. Okay, cool. Sounds good. Okay, well, I guess until the next one, Chris. Okay, all right. See ya. Ciao.